This is a video that you'll need as an introduction to the Mastering Physics Part 2 for Chapter 21 on electric forces and electric fields. This second part of this Mastering Physics assignment, there is a couple of questions on dipoles, and I have made a video all about dipoles, the definition of dipoles, what happens to dipoles when you put them in electric fields, and what their energies are. So you definitely want to see the YouTube video that I made for that, which is on the D2L site under YouTube videos. Now, the rest of this assignment is all about finding electric fields due to continuous charge distributions. Due to continuous charge distributions. What that means is distributions. We're no longer dealing with point charges. We're now dealing with larger shapes of charges. So what we've done so far, we've done one charge creates an electric field, depends on that point charge value, where R is the distance from here to here, the point of interest. And we've done that for multiple point charges as well. But what happens now if you spread out the charge over a big blob? Okay, and so what you have to do is you have to treat this big blob of charge as millions and millions of tiny point charges. And so what you have to do is divide this blob into little tiny point charges, which we're going to call dq. And at any given location where you want the field, each little dq will have its own little bit of field dE. But that's only the contribution from that little bit of dq. You then have to do that for every other little bit of dq in this charge distribution. So this little dq, you would have to do, it would have a different R. This would be R for the first one, R1. This, if that was dq1, and if this was dq2, then you would have a second R, R2, and you'd have a different field, dE, pointing in a different direction, dE2, which would depend on how far away you were from dQ2. And you continue this such that the net field is the summation of all the little bits of field. Now, this integral sign is not an accident that it looks like an S, because it means summation. And you're adding up all the little dE vectors from every little bit of dq in the charge distribution. Now, in general, that's a horrible process because adding vectors is pretty messy. You can write this in general in terms of components. So you would have to do the x component, and it would point in the I hat direction. You'd have to do the y component in the y direction, and then you would have to do the z component for every single one of those little dEs to get the net field. Now, we're never going to do one where we have z. We will do ones where we're going to have an x and a y, but we're also choosing distributions that are pretty simple symmetry-wise. Okay, so the distributions that you're going to have to know how to do the integrations for are the rod, the ring, the disc, the curved rod, and the non-uniform recharged rod. Now, I've made a video for every single one of these. I would normally spend 2 or 3 lecture hours going through these, and I would definitely ask one of these derivations on a midterm, which means I will definitely ask one of these on your oral exam. Okay, so what this means is if you have a charged rod like this, you need to be able to figure out what is the electric field here. If you have a ring, that means literally like a ring like this of charge. And we want to know what the electric field is somewhere on the axis running through the center of the ring. The disk is just exactly that, a disk, very skinny disk, something like this. We want to know the field out here, distance x from the center. This is distance x from that ring, and this will be a distance. Usually we call this distance d, we don't call it x. So there's the rod, the ring, the disk, and then a curved rod would look like this. And we want to know the field here, the ring. And then a non-uniformly charged rod, that means that the charge distribution is not the same. So it might get more densely charged as you move along. So as you go, it would suddenly become very different density. And in that case, we have to define something called the linear charge density. So I've made videos of all of those. You're asked to work with those derivations in the Mastering Physics assignment. And that is a pretty big chunk of this chapter and also of the course, because we'll do a similar kind of activity when we get to magnetic fields. Okay, so that's really all I want to say about that right now.